Hi, good afternoon, everyone. Like she mentioned, I'm working with Citi as part of the strategic surveillance. So I lead the AI strategic surveillance there. So today I'm going to talk about unmasking the unexpected, which basically means identifying outliers using the power of large language model. Okay, is it moving? Oops, sorry. Yeah. So the agenda for today, we'll start with a brief introduction of what is an anomaly. Then we'll look at some of the traditional approaches that we have for identifying these anomalies. Then we'll look at what is an LLM and how we can leverage LLM to identify some of these anomalies. I'll talk about some of the real world case studies that are existing today, and finally we'll close with some of the challenges that we see. So let's get started. So I was actually trying to find a good definition for what is an anomaly, and this is what I could come up with. Everything is an anomaly. So if you think about it, let me tell you this. So I came here today, traveling by a tram. So this is the first time I'm traveling by a tram to an event like this. So this in itself is an anomaly. So this is something I've never done in the past 35 years of my life. So if you see from a certain perspective, everything is an anomaly. But are we really interested in finding these anomalies? Does it add any value? So the important piece here is to not define what is an anomaly, but to look at what is anomaly of interest for us. So as an AI practitioner, I like to distinguish or rather segregate this into two parts. One, these are anomaly which adds value. So let's say, for example, if you see during school holidays, your travel, the travel demand, the shopping demand increases. So this is something which adds value to the system, and there are companies and organizations which might be interested in these kind of deviations, so that they can provide their services, according to this demand. They can cater their holiday packages according to what the needs are at that time of the year. Secondly, then there are bunch of anomalies which extracts value from the system. So these are the fraud transactions, very good examples, very well-known example, but still it's one of the pressing problems of banks and financial industries today. I mean, however we segregate, the crux of the matter is we are trying to find a needle in the haystack. Sometimes the needle is big in size, but at times or most of the times it's very small in size, which makes this process very difficult. Now we have had certain approaches to identify these anomalies, which is what I called as conventional approaches, or more rightly, this can be mentioned as the machine learning approaches that we have had to identify these anomalies. Uh, these are the three basic approaches that we have today: your density-based method, clustering method, and Bayesian method. Let me give you an example. So, sometime back, about 4 to 5 years back, I was working on a problem which involved identifying lanes in a particular road. So this was for Google Maps, that we are trying to predict the number of lanes that are present in a particular highway or in a particular road. Now this can be a challenging problem. I mean, you can either manually go and count each and every road and the number of lanes that it has, or use some kind of algorithm, some kind of mechanism to automatically detect the number of lanes. What we did was we utilized vehicle GPS data, their angle, their velocity and stuff, to identify the number of lanes. Back then, we didn't have a lot of deep learning and large language models to utilize. So what we did was we used one of the density-based algorithms in order to identify the number of lanes in a particular road. The problem with that was we had to make a lot of assumptions while doing this. Like, for example, we assume that if there are at least two vehicles that are found in a particular lane, then only we consider that as a right lane. Secondly, there were observations, or there were inaccuracies in the GPS data itself. We could see some of the vehicles being kind of predicted outside your width of the road. So in order to eradicate those inaccuracies, we had to cluster these vehicles together. Another was we had to take an assumption of how much the width of the road could be. So these are some of the assumptions which we had to make in order to build a system which was able to accurately identify the number of lanes in a particular road. Now, if you see this, if we had some of the advanced algorithms that we have today back then, all these assumptions would not have been needed. We could have easily used some of these algorithms to identify what is the best assumption given the data that we have. So what are the challenges of using this convolutional approach? The first and foremost is the data quality. So all of these algorithms depends on the data that you supply to it. It's a very well-known proverb which says, garbage in and garbage out. So if the data quality is not good, all of these algorithms will suffer. Another thing is none of these algorithms can actually handle high dimensional data. So if you have too many dimensions in your data, these algorithms will struggle to find these anomalies. Next is signal to noise ratio. As we all know, we are trying to identify anomalies which are very rare in nature. If you think about it, if you're trying to identify, let's say, a market risk, in that case, you might not have any market risk that is existing in the past. Let's say if you want to identify insider trading or collusion, these kind of risks are very rare. So it's very low signal to noise ratio, which will lead to challenges in using these algorithms. Last is continuous retraining. All these methodologies are static in time. So you take the data at a particular point in time, train your algorithm, and utilize that particular model to identify anomalies. Now the challenge with this is every time a new scenario has to occur, you have to retrain your algorithm with the new data. Now in order to overcome this problems, what we looked at is the large language models. Now today we have a lot of large language models. So this is just a summary of it. We have definitely more than this. Let's address the elephant in the room. What is a large language model? For me, large language model is nothing but a text-based system which takes a text input and produces an output as you desire. It could be a sentiment, it could be classification of the text, or it could be summarization of the text. What differentiates a large language model with the conventional text-based system is it has already seen and been trained on a very huge data set, maybe millions and billions of text inputs in terms of articles, books, and various other stuff. So that is the power of large language model. Now, how do we utilize this large language model to identify anomalies? One of the advantage of large language model is it is able to establish a semantic reason. It is able to establish semantic reasoning. Let me give an example for this. So Tesla faced this problem some time ago where the self-driving cars were getting confused with the signals that were present on the road. I mean, they were able to identify signals, but there was one scenario where a truck was carrying a signal, apparently for the repair of the signal, and the self-driving car assumed it to be a real signal and made necessary action. Now, if you think about this, this is an anomaly. This wouldn't occur in day-to-day basis, but there should be a way to differentiate between a signal which is active working and is there to either stop or pass the vehicle, as opposed to, let's say, a poster of a signal on the road, or a truck carrying signal for repair. Now, in order to do this, they utilize the large language model. So what it does is, whenever a picture of a signal comes to the system, it is converted into a description and it is given to a large language model. Now, this LLM is able to put that into the context and identify whether the signal is actually an active signal or a poster of a signal that is being put up on the billboard. So this is how the fusion of your large language model with the use case of anomaly detection can help you identify some of these abnormalities or deviations from the normal. Now, the advantage of this is versatility. Now, this is the biggest advantage of using a large language model. With the traditional method, you had to build a bespoke model for each type of anomalies that you wanted to capture. But with large language model, you can utilize the same model with variety of tasks. Let's say you build a model to identify fraud. You can use it for AML. You can use it to identify surveillance risk. Accuracy, as we all know, large language models are drastically or comparably more accurate as compared to your machine learning models. Complexity, by complexity I don't necessarily mean the complexity of the model, but the complex pattern it is able to decode within the data and segregate it from the commonly occurring occurrences within the data. Let me delve some time on this use case. So this is a large language model that we use for fraud detection. So I've taken a toy example to explain this. So what we essentially did was, so this is how the data look like. It has all the transactions that you want. In a typical scenario, what you would do is use a supervised algorithm in order to distinguish your fraud transactions from your genuine transaction. Now, if you see this, the fraud transaction, the first transaction that I've kind of highlighted here, is very similar to all the other transaction in terms of the location. It's California, the type, it's internal and external. So how do you differentiate between such a fraud transaction which is very similar to how a genuine transaction would be? So what we did was we used prompt engineering. So using this data, we generated prompts in this template where we simply convert each of these features into a text-based feature, where we tell the model the location of this particular transaction is California, the amount is 1.5 million, and it was sent externally. Now this is sent to a AI system, which is nothing but your LLM. It generates embeddings, and then that embedding is used to detect a fraud transaction. Now there are two ways that you can use this embedding. One is using your conventional approach. Let's say you use some kind of distance based algorithm, like for example cosine similarity, to see if this particular text is very different from the other genuine transactions that occur in the system. Or a more dynamic way of doing this would be is to continuously stream the data. So this overcomes the challenge that I talked about of continuous retraining of your machine learning based system. So in this, you dynamically train the system. Each transaction that comes into the system, you feed it through this workflow. It is converted into a text, and that text is converted into a vector. Now what the system does is, for each transaction coming in, it tries to compare the transaction with all the previous transactions that it has seen, and comes up with the maybe a probability score of its outlierness. So that way you don't need to actually retrain your system every time you see a new data. At the same time, it is continuously learning as it is predicting these fraud transactions. Okay. I mean, yeah, large language models, yes, can be beneficial. Can give you a kind of a major advantage as compared to a machine learning models, but there are challenges to of using this. The first and the basic challenge is interpretability. I mean, these large language models are also known as black box models. So explaining the output that it produces can sometimes be very difficult, and this becomes more challenging when you're trying to get a buy-in from your business stakeholders of using these kind of models into your system. Next is ethics. Now, if you're not able to interpret these models, it becomes difficult to put your trust on it. Can you believe the prediction that it is making? How do you identify whether the prediction that it made is correct or incorrect? The third is evidence. So this is one of the major area of research at the moment. So recently, or rather sometime back, one of the Google engineers claimed that one of the models that they have developed has become sentient. So it's actually conscious, as a human would. Now let's take a step back before we ponder over whether AI systems are conscious or not. Do we have the right set of parameters to say whether a system or a human is conscious or not? Now, there's a major research that is currently happening to identify what sort of parameters we should look at in order to identify whether a particular machine or a particular AI system is sentient enough or not. On the other side, there is a challenge of hallucinations. It is a kind of a well-known saying that these large language models can hallucinate and produce random outputs as well. So if you're not able to interpret it, if you're not able to believe it, how would you know whether it's hallucinating and giving you the right output as you need? Last but not the least is the practical challenge of scalability. All of these has shown advantages when used in experimental setup. But when you try to actually use this in your production grade systems, there are a lot of practical challenges that comes with it, with respect to the resources that it uses, with respect to the time it takes to identify these anomalies, so on and so forth. Having said that, all is not lost. I mean, given the pace of the technological advancements, I'm sure we'll be able to overcome these challenges sooner rather than later. So that's all from mine, and I'll be glad to answer any questions that you have.
Thank you. Thank you so much. The last presentation before lunch is always the hardest. I find it interesting that we're looking for sentience at a time when we have more humans alive than ever before and potentially more brain power in those humans. So it's an interesting thought there, but I'm going to hand over to you because it's just before lunch and I know many people would be very happy to go eat.
Yeah, if you could just drill down into one of the things you said, the streaming case where presumably you're altering the weights of the model as it gets more information.
Yeah.
It's interesting, but how do you put that against your other requirements to be able to explain things, to be able to audit, and to be able to perhaps like have idempotence to be able to demonstrate you didn't just do something random?
No, I think that's an interesting question. That's one of the challenges of using some of these large language models, that these are unexplainable. Now, coming to the example of actually using this in real time and training it dynamically, I think one of the ways that we can do is, as you would explain a static model, whenever it produces an output, let's say for example, how different that output is to your previous example, or how close it is to one of the previous example which was let's say predicted as a genuine observation. If you're able to make that distinction and identify the features which led to maybe scoring this more risky as compared to your other observations, I think that could be one of the ways where you can actually in real time also explain while you're making the prediction and the model is learning. Another way could be, while you're making these explanations, there can be a human intervention in the loop where the human kind of validates whether the prediction made by the model was correct or not, which can be fed back to the model, and it can learn from that human intervention as well.
Or my other favourite is the vendors who have AI that assess the AIs. And when I asked who assesses the AIs that assess the AIs, they didn't get that I was just making a joke. I mean, it really is a thing.
Turtles all the way down.
It's turtles all the way down. If there are no other pressing questions, there's a pressing question over here. It's a very, very enthusiastic arm prior to lunch. So we'll just take your one last question. Thank you.
So my question is about controlling biases that are inherent in pre-trained LLMs. Because let me tell you, I am a Eastern European young woman, and I don't want a model that was trained on Reddit and Wikipedia to be deciding whether I qualify for a mortgage or not. So how do you control for that when you talk about fraud detection or when you talk about any type of anomaly detection?
Yeah, definitely. There is this problem of bias, and it's a very well-known problem. I would go back to the previous answer that I made. Although these systems are good, they are performing good, and we have seen the output that we get. It's more human-like. But having a human intervention in between is what will differentiate between entirely trusting the prediction made by the model and using that prediction to make decisions. So if you have a human intervention, and if you're able to explain why a particular, let's say for example, let's say a loan application, if your loan application was rejected, if your model is able to explain that why it was rejected, and there's a human intervention which is able to validate whether the rejection was made on valid grounds and not on maybe your ethnicity, race, or religion, if you're able to do that, I think you can overcome that bias. So you would eventually need humans to make some of these decisions, but what can be automated is the data processing and identifying the features which could help us segregate your anomalies from the genuine transactions.
There's an amazing book called Against the Gods about the history of risk, and I think that fundamentally banks need to change how they do business, but that's a broader question because the models that they use now are based on statistically possible and acceptable risk. So for example, if you're married, you're less risk at defaulting on your mortgage than if you're in a de facto relationship, just say. But there are also other indicators that I would argue that they should be using that would show that certain people from certain demographics may actually be more likely to repay their mortgages and could in fact be benefiting from some of these changes. So I think there are a whole lot of hard conversations to be had which may change some of the long-term paradigms in this space. But before lunch, that's a lot. So everyone, have a great lunch. Does everyone know how to find their way out of the building the quickest way? Try to avoid that wall is my recommendation. Go left out here. And enjoy the rest of the summit. Thank you.
Thank you.
Thank you so much.